Have you ever stopped and wondered why you can refreeze a melted ice cube, but you absolutely cannot uncook an egg? I mean, it's a simple question, right? But the answer is fascinating, and it gets to the heart of the secret personality traits of all the stuff around us. So today, we're going to be detectives. We're going to solve the mystery of why some changes are reversible and some are forever. It really all starts right there in your kitchen. You take an ice cube, it melts, you pop the water back in the freezer, and boom, you've got an ice cube again. No problem. But then you try to unfry an egg. You just can't. It's impossible. So what is the deal? Why is one of these changes so easy to undo while the other is totally permanent? Well, the answer to our whole egg mystery lies in understanding that matter, all the stuff in the universe, has two totally different ways of changing. You can think of it like this. A substance has two basic moves it can make. One is kind of like putting on a disguise, and the other is a complete transformation into something new. Okay, so first up, let's talk about physical properties. The easiest way to think about these is like a substance's ID card. They're the core characteristics you can see or measure without actually changing what the substance is. We're talking about things like color, density, how hard it is, or even the exact temperature it needs to melt or boil. So when we talk about a physical change, it's just a change in one of those ID card stats. It's basically a costume change. The appearance is different, maybe it's a different shape or state of matter, like solid to liquid, but the fundamental identity of the substance is exactly the same. And here's the key. These changes are almost always reversible. So for example, when a candle melts, right, the wax goes from solid to liquid, but it's still wax. Or when you dissolve sugar in your coffee, the sugar crystals seem to disappear, but really the molecules are just kind of hiding out in the liquid. In all these cases, the substance's identity hasn't changed one bit. That's a physical change. Now, let's look at the other side of the coin, chemical properties. This is where things get really interesting. A chemical property is all about a substance's potential to undergo a complete and total transformation, its ability to become something entirely new. We're talking about its deep-seated tendencies, like how flammable it is or its tendency to rust. And when a substance actually acts on that potential, that's what we call a chemical change. And listen, this is no costume change. This is a whole new character showing up. Burning a match, an apple rotting on the counter, or our friend the egg being cooked. These are all chemical changes because totally new substances are being formed. And you can't go back. All right, so now that we know the difference, let's put on our detective hats for a lightning round. I'm going to give you a scenario, and you gotta figure out, is the change physical or is it chemical? Let's do this. Okay, first up, our melting ice cube. When ice melts, it becomes liquid water. But here's the question. Is it still water? Yep, absolutely. It is still H2O, just in a different outfit. Since its core identity is unchanged, this is a classic textbook physical change. Case number 2, a rusty iron pipe. What's happening here is the iron is combining with oxygen in the air to form something new, iron oxide. We just call it rust. Now, is rust the same thing as iron? Not at all. It's a brand new substance with totally different properties, so that makes this a chemical change. And now for the moment of truth. Let's solve our big mystery, cooking an egg. The heat from the pan causes the proteins inside the egg to totally break down and rearrange themselves into new structures. You can see it, you can smell it, you can taste it. It's an irreversible transformation. Case closed, cooking an egg is a chemical change. Okay, so we've cracked the case of the two changes, but let's add a new layer to this investigation. When we're looking at all these properties, does the amount of stuff we have actually make a difference? Does size matter? Let's think about this with a question that you probably don't want to test out for yourself. What's going to cause a worse burn? A single tiny drop of boiling oil or an entire pot of that same boiling oil? The answer seems pretty obvious, but the science behind why it's obvious is really, really cool. So this gets us to the difference between intensive and extensive properties. The temperature of the oil is an intensive property. It's completely independent of the amount. That one drop in the whole pot can be at the exact same temperature. But the total amount of heat energy, well, that's an extensive property. It depends on how much stuff you have. That big pot of oil contains way, way more heat energy, and that's what causes the much more severe burn. Now, you might be thinking this is all just, interesting theory. But understanding these properties, especially the chemical ones, has some incredibly important real-world applications. In fact, it can literally save your life. You've probably seen this symbol before, maybe in a science lab or on the back of a chemical transport truck. It's called the NFPA 704 hazard diamond. And what it is a super quick visual summary of a substance's chemical properties and all its potential dangers. Each color gives you a critical piece of information just at a glance. So the red diamond up top, that tells you about its flammability. The blue one on the left indicates any health risks. The yellow on the right signals how reactive or unstable it is. And that white diamond at the bottom, that's for any special hazards, like maybe it's something you really don't want to mix with water. And each of these categories is rated on a scale from 0 to 4. 0 means pretty much no hazard, but a 4? Well, a 4 means this stuff is extremely dangerous and you need to be very, very careful. It's an entire safety system built on just understanding a substance's chemical identity. So we've seen how these properties define what a substance is and how they even keep us safe. But their most powerful role is in how they bring order to the entire universe of matter. You see, all these physical and chemical properties, they aren't just a random list of facts for every substance. They actually form patterns. And by understanding these patterns, chemists have been able to create the ultimate cheat sheet for every single element we know of. Just for example, if you look at one single physical property, how well an element conducts electricity, we can immediately start sorting them into these huge major classes. Metals are fantastic conductors. Nonmetals are terrible at it, and metalloids are somewhere in between. Simple as that. And all of this leads us to one of the most beautiful and powerful tools in all of science, the periodic table. It is not just a random chart of elements, no way. It's a masterpiece of organization, specifically arranged so that elements with similar physical and chemical properties all hang out together in the same neighborhood. And as the source material puts it just perfectly, the entire point of the table is to group elements with similar properties. So just by knowing where an element lives on the table, you can start to predict its personality, how it's going to behave, how it will react. It all comes back to its properties. So from the simple mystery of a cooked egg all the way to the elegant design of the periodic table, it all boils down to that one key distinction: physical versus chemical change. The next time you see a banana browning on your counter or bread rising in the oven, you'll know you're seeing chemistry in action. So here's my question for you. Now that you know what to look for, what chemical changes will you spot in the world today?